So we are live now. You can start.
I can start.
Yes, please.
Yeah. So good afternoon to all, and a warm welcome to this webinar. Just to introduce myself, I'm Indra Sen. I'm an assistant professor in the Department of Earth Sciences in IIT Kanpur. I joined the institute in 2014, and since then, I'm actively working in the field of Himalayan glaciers, and particularly the large river systems. So today I will be mostly talking about the impurities in the Himalayan glaciers, and when I say impurities, it's mostly the particles that is transported from the Indo-Gangetic plains, different kind of emissions, and not only that, where they are coming from and how they are coming from. So said so, I will start my talk. Let me just share my screen. Yeah, so the talk would be all about surface impurities in the Himalayan glaciers, its sources, pathways, and of course we do see a lot of spatial variability, and that I would try to kind of figure out, try to tell you how and why these things are. So, and before I start, let me acknowledge all the funding agencies. These works would have not been possible without the constant support from Department of Science and Technology, from the Climate Change Program, from the SERB, ACRB, Science and Engineering Education Research Board, Ministry of Earth Sciences, of course, for funding us to work on the large river system in the Himalayan region, Indian Institute of Technology, National Academy of Sciences, USA, and as well as Intel, where they are supporting and in various aspects. And of course, the most important, all my group members, the postdocs, the PhD candidates, the BSMS students, and of course the lab technicians and all. So throughout this presentation, I would mostly talk about two research topics related to Himalayan Glacier, which are part of my PhD student, Mr. Sarwar Nizam, and Mr. Arijit Mitra's PhD dissertation. So again, I would specially thank them, because I'm just telling every one of you about their work. So when it comes to Himalaya, I think Himalaya is a fascinating place. Of course, it is well known globally for the high altitude peaks. There are several of them. People who love tea, for the Darjeeling tea you drink, the one horned rhinoceros, which is only exclusively found in the Terai belt of the Himalaya, the Royal Bengal tiger. You have this Jim Corbett National Park and many others. And then some of the highest motorable roads in the world, as you can see, the Khardungla top on the right side. And of course, for us as an earth scientist, we have large rivers, the Ganga, the Indus, the Brahmaputra, and of course, a lot of glaciers, and the Himalaya and its surrounding. That's why it's called the third pole region of the world. So in this talk, I would mostly focus on the Himalayan glaciers and the impurities on them. And also I'll briefly talk about some of the other ongoing projects on the rivers of the Himalayan, and in general the Himalayan source to rivers. So to start, of course, as you all know, the Himalayas are the most fragilized in terms of climate change. And when I talk about climate change, it is not like I'm talking about a million or tens of thousands of years. My family itself can feel all these generation. So as you see, my great grandmother, my father born in the 1940s, my daughter. So they actually, this 4 generation or 5 generation has seen changes, and it's it's unprecedented change that we see in the human history. The global sea level has rose. The summer Arctic sea ice area has decreased. So if we look at early 1900, it was almost 12 million square kilometer, and now it is almost like 6 million. So there is a 50% reduction in the Arctic ice. The ocean heat content has gone up. The sea surface temperature has gone up because of various reasons. The surface pH, and that's why ocean acidification is a big issue nowadays. And the same thing as we see it's in the Himalaya too. The glaciers are melting. Say for example, this paper by Bolsh et al. In 2012, where you can visually see that the glaciers are retreating. Some are, of course, at steady state, but there is a overall retreat in the glaciers, small or large. I'm not getting into it, but there we see a retreat. And The first, of course, question comes into mind that why these Himalayan glaciers retreat. Of course, one aspect would be the climate change, but my research mostly address on the other smaller aspect maybe, and that is the glacial surface impurities. Now, when I say glacial surface impurities, it can be of many form. It can be the dust, it can be the soot, and when I say soot, it is mostly for different community use different terminology. Like the atmospheric community, we use black carbon. As a geochemist, I use organic carbon. So basically, it's a source of carbon, microbes, and all of them have a certain role, because ultimately what they are doing is basically they are absorbing heat, and that heat corresponds to melting the glaciers. So now, as a geochemist, since we look at very low level concentrations of chemicals, of course the ideal would be to analyze snow and ice component, but we are looking at picogram level of elements and their isotopic composition. So it is simply analytically it's very challenging, and it's not really very easy to measure them. So that's why we actually focused on some kind of naturally occurring debris on the ice surface, which is again dark in color, which is called cryoconite. So cryoconite, if you look as the definition of cryoconite, it is basically it's a mixture of your dust, soot, and again soot means organic carbon, and microbes. So essentially what the surface of the glacier, you will see like dark colored spots which are pitting the surface of the glacier, and these are actually absorbing heat. And we thought, why not let's look at these glacial debris, because essentially these are reflecting many years of accumulation on the surface of the glacier. So all our geochemical work that we will show here on the glacier surface is actually related to the cryoconite. So as I was saying, the concept is very simple. If you have fresh white snow, they will reflect most of the light, and as you see on the left hand side, 90% of the incoming sunlight is actually reflected back. While if you look at the on the extreme right side, you see contaminated snow, old, only 30% is reflected back, and sunlight means energy, and if your white snow is kind of absorbing those energy, of course it will enhance the melting rate. So that is why these impurities are extremely important. And even within those impurities, different impurities have different role. Say for example, a black carbon, which is again a part of organic carbon, it is almost like it heat absorbing capacity is almost 100 times more than the dust. But in general, any dark color material on the surface of the white snow or glacier will actually absorb heat, and it will kind of melt the glacier. So given this background, and also we all know, I think it is nothing new, that there are many reports shoot on Himalayan glaciers, South Asian, because these are the hotspot of carbonaceous aerosol emissions, dirty snow, Hessian glacier. And it is not only Himalaya, it is, I think, these dark deposits have been seen in Arctic and Antarctic, and which are mostly kind of related, and this has been related to the melting rates. So this is universal, and if you really look at the Indian map out here, and you will see that how the difference carbonaceous aerosols emission has increased over the last 30 to 40 years. So given this backdrop, we thought that why not we kind of try to look into three primary things, and entire talk will be structured around that. So firstly, we will look into the geochemical information on the glacier surface, that is dust and other impurities in the ablation zone of the Indian glacier, which is still unexplored, underexplored, and the origin, the transport pathway, the spatial variability of organic carbon and other anthropogenic particles on the ice surface. So I will talk about three. One is about of anthropogenic particles, and when I say anthropogenic particles, I mean dust particles, anthropogenic dust particles, as well as organic carbon, because there are different forms by which through they are emitted. And secondly, I will talk about their pathways. So how actually they reach there, what controls them, because that is also essentially very important to kind of address, in addition to identifying the sources, what actually controls them, how they reach there, those spots. I think that is also very important. And of course, the third one, it's spatial variability. Like, for example, as I come next slide, whether the studies that we do in the Western Himalayan Glacier is true for Central and Eastern. So the entire talk would be structured in these three forms. So what are their sources, how they are reaching there, and what sort of variability exists in the Himalayan glacier system. So that way, and given that, I would kind of start the research talk out here. And again, thanks to MOES for giving this wonderful opportunity for me to talk to everyone about our work that we are doing in IIT Kanpur. Again, this work was part of my student server's PhD dissertation. So what we did is actually as a glacier site, we choose Chota Shigri Glacier, and I would also like to thank Farooq Azam out here for leading the field campaign. So we went to the glacier and we actually collected this glacial debris that I was talking about. So if you look at figure number C, figure number B, you see these circular pots, circular glacial holes, which are actually called cryconite. These are few centimeters in scale, perfectly round to spherical in shape. And of course, by the color, you can look at their dark in color. So what we did is, throughout the ablation zone of the glacier, we actually collected this cryconite debris, as well as we collected moraines, local rocks from the surrounding. So on this map, what you see, the blue colors are basically your cryconite holes, which corresponds to C and B in the figure, and the yellow color symbols corresponds to the local rock that is there in the surrounding sidewall region. So this was the field trip that was done, and the samples were collected. And now we will come to look into their detailed geochemical as well as isotopic composition. So this is the kind of methodology that we followed, and not only that, because as I said that we are also interested to find out that how these particles actually reach those sites. That means, where are they coming from? So to know that, we also have to do a lot of other sampling, like we called it as source members, end members, that could possibly contribute to those cryconite holes. So if you look at the sample collection, it was one of the most exhaustive sample collection that what we did. We sampled the cryconite and the moraines, as you can see on the left. Then we also collected aerosols, from a high altitude aerosol observatory that we set up in Harshil. It's a remote village in the central Himalaya in the Uttarakhand state of Uttarakhand. We did in the lab in IIT Kanpur, we did engine exhaust experiments, because ultimately all these black carbons are emitted through the engine exhaust. And we were lucky to have the engine lab out here in the mechanical engineering department, where we actually fitted the filter behind the exhaust tailpipe of vehicles to collect the particles, which are mostly the black carbon particles that are coming in the engine exhaust. We collected coal samples, we collected biomass samples, from throughout the Indo-Gangetic plains. And then, it's a lot of different samples. But again, the idea was to kind of figure out the source of the glacial debris and who all are contributing to those glacial debris. So given that in mind, we also designed a lot of state-of-the-art analytical tools that we have used. Apart from the routine trace metal and major oxides, we looked into lead isotopes, the osmium isotopes, where I have a lot of experience, almost 10 years on the osmium isotopes. And also the organic carbon thermal reactivity, and I'll come to it one by one. So both in terms of elemental analysis, radiogenic isotopes, as well as ramped pyrox oxidation, and I will come to it what ramped pyrox oxidation is. So we took the cryconite, and you will see throughout the presentation there are three fractions in it. When we say bulk, it is less than 3 millimeter size. When we say fine, it is less than 63 micron, and hand-picked ones are greater than 3 millimeters. So we also looked into the different size fractions of this cryoconite to have a better understanding that where these anthropogenic particles are coming from. So before I do proceed, keeping the wider audience in mind, I just thought of sharing few of my teaching slides about isotopes. Why these radiogenic isotopes are excellent tracers, particularly for tracing atmospheric processes, tracing provenances. Because if you look at any of the systematics that I will be using throughout, that the lead isotopes, the samarium neodymium isotopes, the rhenium osmium isotopes, so there are two components to it. One is your non-radiogenic part. So in this case, it is this 144 neodymium and it is 204 lead. And the other is the radiogenic component. So for example, 147 neodymium, decays to 143 neodymium. Similarly, 238 uranium decays to 206 lead, and so on. 235 uranium to 207 lead, and 232 thorium to 208 lead. But the interesting thing to look at here is the half-life of all these isotopic systems. So they are of the order of billions of years. Now that makes it very interesting because we are trying to trace superficial processes. We are trying to trace kind of use this as tracers of where they are coming from. So technically, the scale that we are not looking into a evolution of a mantle rock or a evaluation of a crustal rock. We are trying to just try to identify the signature and trying to correlate with known signature, and that is a fundamental of provenance tracing. So it can be kind of kept constant. These are actually behaving as conservative tracers. So these numbers will not change. Say for example, if you take an a iron ore with lead in it, and if if you are purifying iron through the process of smelting or anything else, these lead isotopes will show any very negligible change in its isotopic ratio, which means that these will throughout the process from emission to transportation to actually deposition, these isotope ratios don't change. And it is very different from those stable isotopic system which can undergo different physiochemical, biological fractionation. So they can be considered to be constant, and that is the reason they are so widely used in provenance tracing. And this will give you one more good example in how you can use osmium isotopes. Again, 187 rhenium is the parent isotope which decays to 187 osmium, and it's a standard 101 isotope geochemistry isotope in the geochemical formula. And what you see on the left is the different ranges of N members. So for example, if you look at this study, we have gondwana coal, which has a very high radiogenic 187, 188. We have vehicular exhaust, which has an extremely unradiogenic 187, 928 signature. So the vehicular exhaust is on the left corner of the figure. You have tertiary coal, and then you have a cryoconite. What we saw, it has a huge range, covering from almost 0.4 to 1.3. And then on this anthropogenic, you have liquid fossil fuel, municipal waste, chromite, PGU. But what thing actually makes this systematics or any provenance study in so-called much more complicated is because of overlapping range. Say for example, if you draw a straight line, a vertical straight line over a value of fossil fuel, can be contribution from black shell, can be contribution from high Himalayan crystalline sequence, global river, desert sand. And if you look at the range at 0.2, it can be vehicular extract, terrestrial coal, municipal waste, PGE, catalytic converter, ultramafic rock, cosmic dust, volcanic aerosol. So it is not that straightforward that for any provenance study, what you really need is unique N members, and then only you can deconvolute the source where they're coming from. So that is the problem, and that is the reason we really need to rely on multiple tracers, multiple chemical tracers, multiple isotopic tracers, so that we can tease about these different components of this complex systematics. So given this backdrop, I think let's get into a more straightforward way, where we looked into the glacial debris. So out here, as I said, you remember we have three different fractions: the bulk moraine, fine moraine, and cryconite. What you see here is, and these are all normalized to the local rock. So any line which is perpendicular to the line of 1 is basically essentially a local rock composition. So what the bulk rock, of course, as you would expect, it resembles the local rock composition, and even the cryconite and the fine moraine fraction also looks very similar, and similar in the sense of similar geochemical pattern. And the blue box actually tells you the similarity. That's what you've been highlighted out here. But mostly these are and if you look at enrichment factors, again, these are just very simple calculations. Enrichment factors are calculated based on a crustal element. In this case, we have used scandium, because scandium is not there in anthropogenic sources, and any line below 1 is basically natural, and any line over 1 is anthropogenic. So out here, what we see, it's a very little enrichment of trace elements are there on these cryoconites. So I will quickly go through them. And again, these are traditional uh, discrimination plots, where you plot the chemical index of alteration. So what you see here on the x-axis is Al2O3 on the AB, on the ternary plot I'm talking about. So on the A apex you can see Al2O3, and on the on the other side you use to calcium oxide and sodium oxide, and on potassium oxide. So basically what this says, that what is the extent of weathering, because the more the weathering progress, you get more enrichment in Al2O3 because of clay formation. And when we plotted our kaolinite, when we plotted our cryoconites, what we saw, they are mostly falling on the weak weathering pattern, and the source rock is mostly the high Himalayan crystalline sequence. That of course is very much expected out there. But the interesting part is what we saw, if you look at the lanthanum by cobalt and the thorium by cobalt, a very simple thing what we see, that the cryoconites, which are circle field pink color circles, they are actually tending a little towards a mafic flow. There is also a mafic component that what we see. And similarly, if you look at the rare earth element and yttrium, your cryoconites, which are the solid black color circles, they actually fall in between the bulk moraine and the fine moraine. Again, that what you would expect. But I think the key message that what we see here, as reported elsewhere, these materials are mostly locals, and of course I would expect that. But at least the major element, trace element, all points out towards a definite more crustal contribution. Now, if you look at the rhenium osmium and the 187 by 188 osmium, as you remember my previous slide, the cryoconites has a large range from almost 0.4 to 1.4, and just to give you a reference, the upper continental crust has a value of 1.2. So clearly there is some variability, and out here what we have plotted, on the y-axis you have elevation. So we collected samples from the snout of the glacier across the elevation. So almost from 4,500 meter we went up to close to 5,000 meter above sea level. So what we see is there is a difference in the geochemical signature spatially, from the snout to the top of the ablation, close to the 5,000 meter elevation. And that means that it is not a constant input. So the inputs are changing time to time from elevation across. So there is a lot of spatial variability even within a single glacier. I'm not even talking about different glacier. So this is a single glacier where we have sampled the kind of the elevation profile, what you see here. And we do see a lot of variability within a single glacier. I think that's a very interesting observation that we saw. In general, we would have expected the single isotopic value. So which means spatial variability do exist even within single glacier system. And then what we do, since we thought that from the major oxide and trace elements, it is mostly crustal, we again, any isotope geochemist would understand, we just did a 3-component mixing calculation. It's nothing fancy. So on A, what you see, there are 3 M members, LM, LR, and UR, where LM is basically your local rocks. UR is your ultramafic rocks, because we saw some sort of ultramafic signature on the trace element systematics. And this LR is some less radiogenic osmium poor mineral phase like aeolian quartz or granite or orthonite, which has very little osmium and kind of intermediate 187, 188. And it's a simple 3-component mixing model we ran, and B is the answer to it. So basically the spatial variability what you see from the 4,500 meter to 5,000 meter elevation is because of variable input from different crustal rock material. Again, that is what is expected, but I think the unique 2 things are very first of all, we actually proved how the crustal rocks contribution are varying across the one single glacier system. And secondly, of course, there are no fossil fuel signature. It is very clear from the trace elements, from the rare earth elements, from the osmium isotopes, we don't see any fossil fuel signature. So that is, this is actually under review in the cryosphere discussion. So please comment, because it is still live, and we can revise and again improve this manuscript. Now I will come to the other important isotopic stressors. Again, the concept is same here, so I'm not repeating it, but it's just a different isotopic systematic. So on your y-axis, we see we have you have plotted 206 lead by 204 lead, and on your on your x-axis, and on your y-axis it is 208 lead over 204 lead, and this 208. So what you see here is again different kind of areas, color coded areas, which basically represent different N members possibly, like coal fly ash, local rocks, Indo-Gangetic plain aerosols, vehicular exhaust, leaded gasoline. And again, also the same story holds true even when we use lead isotopes. These are the signatures that what we see in the cryoconite debris are all coming from predominantly the crustal material. So there is no doubt from any point, from any geochemical proxy, that we see fossil fuel signature. But still we thought of looking into, because the atmospheric community is also very much interested in black carbon. And again, I think it's the way we use the nomenclature. As a geochemist, we prefer using organic carbon, because that comprise the entire carbon spectrum. So out here what we did is something called ramped pyrolysis oxidation through my colleagues in Woodsole, where I did my postdoc. So what it basically does, you are not actually looking at a bulk rock 14 carbon analysis. This actually, the RPO methods is basically almost, you can say it's equivalent to of a compound specific 14 carbon analysis. So I think this is really state of the art. So how it works is basically we take a sample and then we heat it up. Say for example, on x-axis you see the temperature range between 100 to from 0 to 800. So at each temperature interval, say for example at 100 to 200, the whatever CO2 is being emitted, we actually capture that CO2 and make a 14 carbon analysis of that CO2. And in that way you are getting much more information that you would get if you are doing a bulk CO2 analysis, a bulk 14 carbon analysis of the sample. And this entire paper is, I would like to highlight, this entire paper is based on 2 samples, because we actually teased about one single sample into like 6 different components. So again, as I'm emphasizing, these are compound specific 14 carbon and 13 carbon analysis. So what you see here is basically what we call the thermogram. Now K stands for Kanpur aerosols. Again, these are PM10 samples, and HA stands for Herschel aerosols. C9 and C14 are cryoconite, and D is your moraine. So we only measure 2 cryoconite samples, but multiple times in a compound specific manner. And what is interesting and what is again expected, so if you look at their CO2 emission profile, what like the normal thermogram, The Kanpur aerosol is very different. It has a bimodal peak, one peak at 300 degree and the other peak at 450 degree. But in comparison, Kanpur and Harshil and all the cryoconite moraine has one single peak around 300 degree. And again, as I said, it is very much expected because Kanpur being an industrial city, in the hotspot of all emission sources, so of course their pattern should look different. So just the thermogram reveals that the cryoconite and the moraine and the Harshil aerosols are very similar, and on the other hand, the Kanpur aerosol is very similar. So now what we did is we actually took this evolved CO2 at different fractions. Say we have one fraction between 100, 200, second fraction between 200, 300, third fraction 300, 400, then 400, 500, 500, 600. So we actually trapped the amount of CO2 evolved at each and every 100 degree Celsius bracket, and we actually measured the carbon isotopes of those those captured fractions. So again, this is what you will see. Given a general audience, I would try to explain it as simply as possible. Again, this paper is just based on these two samples that you see, C9 and C14. So what you see here is basically the RPO fraction, which is FM. Just remember that FM close to 1 means modern, and FM close to the more you go away from 1, it is basically a old age, and it is kind of anthropogenic or petrogenic, whatever you say. So the pink color, so let's look at the left image. So you see these are numbers written in 0.10, 0.53, and these are ages of those trapped kind of fractions of CO2. And K stands for the Kanpur aerosols, and as you expect, Kanpur aerosols have aged carbon like 7 kilo years, 5.2 kilo years, 3.86 kilo years, and so on. But the Harshil aerosols are more or less modern, very young in age. And also one important thing is we also looked into the activation energy of this carbon molecule. Again, a lower activation energy of less than 150 kilojoule per from molecule, basically a mole, sorry, reflects a biospheric source, and a high activation energy of 200 kilojoule per mole and a FM value of close to 0 represents a petrogenetic source. So looking at these, we can clearly say that the Kanpur aerosols have a lot of fossil fuel signature, as it would expect. But the Harshil aerosols, which are again, it's a remote aerosol observatory which we ran for 1 year. It has only, it only gets its carbon from modern carbon sources, mostly biospheric in nature. Now, if you look at the right side, and these are our cryoconite and the moraine samples. These are most of them are modern, but there are few of them which actually have little bit aged carbon, like 6.22 kilo year, 4.01 kilo year. But what we are saying, based on the activation energy and the carbon isotope date and other proxies, these are mostly a binary mixing, what we call, between organic carbon which is coming from rocks and your biospheric source. So again, it is very difficult to kind of explain this on a virtual platform like this. But what we can conclusively prove that the organic carbon that what we see that is deposited on the surface of Chota Shigri Glacier is mostly almost 98.3% of it is being derived from biospheric sources, and only 1.7% is derived from petrogenic sources, and there is no fossil fuel. Based on the activation energy, 14 carbon dates, and as well as 13 carbon isotopic signature, which I'm not showing here, it conclusively again shows kind of repeat the same story. We don't see any fossil fuel signature in the Chota Shigri Glacier. And now that is very interesting, and this has been published recently in Environmental Science and Technology. So if I conclude the source of our impurities on glaciers, on the Chota Shigri glaciers, they are mostly derived from local rocks. Organic carbon is derived from biological sources, and I'm not getting into what sort of biological sources. If you're interested, please read our paper. Where we also use nitrogen isotopes and nitrogen concentration, carbon isotopic data to further, looked into what sort of biological sources they are. And the most important is there is no fossil fuel component that was detected. I think that was quite a different findings, and it is disagreement with many recent findings, and just I have explained you one of them. So now the question, now I will shift gear, and I will talk about how these pollutants actually come there. One is identifying them, their sources, and the other aspect is what controls their movement, because ultimately these emissions are actually coming from the Indo-Gangetic plains. So how these pollutants are getting transported. And again, this is work of my PhD student, Mitra, and this is under review at this time in Science Advance. So what we did is we ran a time series station in Herschel, as I was saying again and again. So as you can see, we have a PM10 sampler, a PM2.5 sampler. We installed a weather station, and we collected weekly aerosol samples and as well as weather station, weather data from this location. And then I think this is the first time series record of, isotopic record of aerosols anywhere on the globe, to be very honest. So what we see, and also that's why, I'm a strong, I would strongly advocate of using time series data, because if you're not doing a time series, you actually lose a lot of trends that are not visible unless you have continuous data. So what you see, I will just give you one or two example again. So if you look at the 208 by 204 lead isotopic record, what we see is, as you know, and on your x-axis you have the time with April, March, June, July, August, September, and so on. So it's a year basically. What we see, only the ash part, look at the ash shaded box out here. The winter samples are very different. Isotopically they are extremely different, geochemically they are extremely different. Only thing that remains same is their mass loading, that is the concentration of dust in air. But the geochemically, one key observation from this figure, you can pick up lead isotope, you pick up neodymium isotope, whichever you pick up, it will only show that the winter samples are very different. Now there is something going on, that the winter samples are isotopically different, and that is what we tried to figure out. And as I said, for this we actually sampled one of the, extensively sampled the Indo-Gangetic plain, from Ludhiana to New Delhi to Kanpur, Jabalpur, Gaya, Patna, Kolkata, everywhere we collected biomass, fossil woods, coal, vehicle exhaust. So it is one of the most extensive study that our group has done almost so far. It has almost like 100 lead isotope data, to be very honest. And then what we see, but after doing all this analysis, what we see, and as I said, the winters are very different. What we see that your winter sample resembles, so you look at these green circles on the left hand bottom corner of the figure. The winter sample resemble more like the local Himalayan biomass, local crustal signature, while the non-winter time more or less overlap with the Indo-Gangetic plain aerosols, the Kanpur aerosols, the Delhi aerosols. So there is a, basically, just looking at this figure, you can clearly say that my non-winter times are more reflecting an Indo-Gangetic plain signature, but my winter time is reflecting more like a local signature. So something is happening which is actually making the winter time samples more local, more crustal, more natural, because of course Himalaya is less polluted in compared to Indo-Gangetic plain. So some process is acting which making the winter samples less polluted than the non-winter samples. And again, if you look at this, the same way out here we plot 206 by 204 on x-axis and 208 by 204. The green symbols are the Himalayan biomass, and the yellow triangles are your winter aerosols that were collected in Herschel. Clearly they are different, they are falling more towards the Himalayan signature, and this is apparently more clear if you plot epsilon neodymium versus 206 211. The non-winter aerosols are completely it's like a scatter in this bivariant plot. There is no systematic relationship. But if you look at the winter Herschel aerosols, they have a very nice positive correlation. So what I'm trying to prove is your winter aerosols are isotopically very different than your non-winter ones. And if you do again some mixing calculation, you clearly know the answer just looking at it. Your winter aerosols have more local contribution compared to the non-winter months. Now that is really strange, because it is strange in the sense, if you look at the, so how can you explain such variability? The most obvious reason would be your change in wind direction. That means you can always argue that, okay, look, during the winter time, what happened, your wind direction was different, and as a result you picked up a different source. But if you look at the local wind direction pattern or the wind speed, there is almost, there is no relationship. This, the size of the symbols corresponds to the lead concentration. Again, please note that the units are nanogram per meter cube. That is, in 1 meter cube of air, how many grams of lead particles are there. And the color coding corresponds to the 206 by 207 signature. So there is no systematic correlation, because that would be the most obvious reason, that the change of isotopic signature is based on either wind speed. Maybe you can argue that the wind speed change, so it has a sorting effect, we can say, or maybe the sources were different. So there is no systematic relationship, and these are based on our AWS data that was installed at the site. And even if you look at the regional wind pattern, I think this is very well established, that Indian summer monsoon times, the wind kind of moves from the southwest, from the southern part of the site. That's the Indian summer monsoon, and the rest is all westerlies, coming from the west. So if you go back, if you remember, so if this is the case, I think the only isotopic difference what we would have expected is during the monsoon time, because the monsoon time reflects this green air mass trajectory. So monsoon time would have been different, and then the rest, then this story would have been perfect. But what we saw, the DJF, that is the December, January, February time, had a very different isotopic signature from the rest. And then I thanks to Vinod V from IIT Bhubaneswar, because it has to do with some climate dynamics. So we looked into the planetary boundary layer height. Again, it is a very well established thing. And what we saw very interestingly, that our isotopes are correlating with planetary boundary layer heights. So if you look at that, the epsilon navium on the upper side representing Himalaya, and on the lower side represents a Indo-Gangetic plain contribution. So said so, I think we propose a very kind of well established theory, but this is, we can prove using isotope data, that during winter times, since your planetary boundary layer is very low, it actually caps the pollutants in the Indo-Gangetic plain. But during summertime, since the planetary boundary layer goes up, which is your green dotted line, the pollutants can expect. And I think this is the first time we tried to quantify how much pollutants can expect, and we saw that the thin boundary layer almost trapped 25% more of this anthropogenic particle. So this is actually under review in Science Advance, and we'll see. And again, I think when we talk about spatial variability, I told you there is a lot of variability between glaciers to glaciers, and again it contradicts many of these studies. For example, in Thorong, Kwengyang, Yolong, which is from the Liekel study, they actually found 50% more fossil fuel, 50% fossil fuel impact compared to our study, where we did not find any fossil fuel input on the Himalayan glaciers. Anyway, this can be debated, and let's see what comes up. So the take-home message of my talk would be the RPO, that is the ramp pyrrole oxidation results show that the organic carbon in the Chota Shibri Glacier is mostly derived from local biomass source, and that is even supported by osmium, lead, trace elements, major oxides data. And this is actually in contrary to all the central and eastern Himalayan glaciers. Regional heterogeneity, and not only regional, even heterogeneity exists in a single glacier. So we have to keep that in mind. And of course, how these particles are transported, we can prove that the planetary layer boundary height dynamics play a major role in the seasonal transport pattern of anthropogenic particles to the Himalayan glacier. And I'm happy to let you know that this was picked up as many news item, including it was mentioned in the DST website, and as was highlighted as a cover page article of Environmental Science and Technology. as well as we were appreciated by the Honorable Minister as well. And to conclude this part, I must thank Farooq from IIT Indore for leading the fieldwork, Akhilendra Pratap Singh for doing the engine exhaust experiment, and Valier Gali for the RPO analysis, Dave Selby for osmium, Vinod for all the atmospheric modeling, and Michael Bizimis and Thomas Mazel for helping with many of these isotopic analysis. To continue, I would also like to highlight the other things that our group is working, other PhD students are working. We are actively working on the Ganga River geochemistry from the source to sink, from individual sampling campaigns to time series records. And this is a recent paper that will come up very soon, where we will show that how the Ganga River actually have geochemically evolved from the source to sink. It will be published. It's in press, so will be published soon. We looked into the response of COVID-19 on the chemistry of large river system, and again we will contradict many, because we really don't see any sort of change in the chemistry of the river. And when I say no change, I mean the heavy metals and all these dissolved inorganic constituents. I'm not talking about dissolved oxygen or other physicochemical parameters. So I'm sure this will also we are actively working on. And also we are working on more fundamental science questions, like through evaluating how the strontium isotopes varies, how the sediments are interacting with water, and so on. So these are the domains that our group is working on, mostly on the Himalayan glaciers and the large river systems. So thank you so much for your attention, and I hope that I have finished in time, and I would be happy to take more questions. Thank you so much.
Thank you, Professor Sen, for an interesting talk on Himalayan glaciers, impurities, and pathways. It was very interesting to listen various aspects. For example, the role of fossil fuel is not very much as it was initially thought by many studies. So we have some questions, and I have posted it through the chat window. So kindly read the question and answer.
So the first question is, what are the degree of representativeness of the N member assigned to UL-LR extractor for osmium isotopes? So I think the osmium isotopes. So again, I think the question is how I think we assign the N members. So the good thing about that since we actually measured the local rock, we measured the cryconite debris, we measured the moraine debris. So these are all we measured in our lab, and using other geochemical tracers, like using the major oxides, using the trace elements, we kind of try to fix the N member. And this is any standard isotope mixing calculation where we assign a value. That can be a unique value, that can be a range. That lot of time we use a range and we do Monte Carlo simulation to it. But yes, so I think these are well representative, because these are actually measured data. We are not relying on any other papers or something. This is what we measured by ourselves in the lab. So the question two from Rahul Sen and Rajdeep Roy. If I understood correctly, you are saying that fossil fuels are not responsible for ice melt in high altitude. Yes, absolutely. And I cannot talk about the entire Himalaya. I can at least tell you about Chota Shigri Glacier. There is no detectable fossil fuel residues on Chota Shigri Glacier. So that means at least the surface glacial debris which actually contribute to melting, it is not affecting the melting rates of Chota Shigri Glacier, because it is not there on the surface of the Chota Shigri Glacier. But I cannot talk about other glaciers, because there have been other studies which shows that 50% of the glacial debris, the black color residues that you see in other central and eastern Himalayan glaciers, these are derived from fossil fuel sources. The third question is, can we identify the impurities through remote sensing techniques? Again, I'm not a remote sensing expert, but these impurities, if you look at a cryconite hole, it is few centimeters scale. So I think it would be a resolution issue, because these are so small in size. But I'm sure there are ways to do it. I think you need to really consult a remote sensing expert. because I know a lot of improvement happened on that field also, because we are able to measure snow thickness, snow depth, snow cover area. So I'm sure this can be also done, but I'm not an expert to answer whether it can be done through remote sensing techniques at the scale we are looking at, because these are really small pockets. The fourth question is, what was the purity level on surface in the Himalayan glacier before impurities? These impurities are detriment. Again, the purity levels on the surface, even on these, so this cryoconite holes by definition are a mixture of soot, dust, most concentrated form. Why we opted for cryoconite, because the analysis I talked about, it cannot be done if the concentrations are very low. It's just analytically not possible. So that's why we thought cryoconite is the best way, because the concentrations are much higher, and if there is a signature, that is the best medium to get some signal out of it. So if it is not even there in cryoconite, I really would not expect any signal on snow, unless you are like filtering like 10,000 liters of snow, and then you will get some signal. But then again, you have to divide it by 10,000 liters. So these are almost below detection limit. So these are pure in terms of osmium, lead, all these impurities. The fifth question is, which factor is more dangerous for melting this glacier, the local pollution or the overall pollution that is happening in the world, like the industrial pollution? Again, I think this is an excellent question. So what we proposed in our EST environmental science and technology paper, it is the local pollution which is actually impacting more, because what we have shown, and please read that paper if you get time. What we have shown using isotopes and atmospheric modeling, that only the local signatures are reaching there, the local biomass derived particle. If you look at the location of Chota Shigri Glacier, it is not really far away from big highways and all, but still those things are not, the fossil fuel signature are not really reaching that particular site that where we have studied. But it is the local biomass, locally derived biomass. Biomass again can also produce carbon particles, like your fossil fuel burning produce carbon particles. Biomass can also produce carbon particles. So they are only being derived from this locally source. It's not that the biomass from the Indo-Gangetic plain is reaching there, because if that reaches there, fossil fuel will be also reaching there. So it is the local level pollution. And of course, you may ask that, what can be the source of, these pollutants, who are burning biomasses there? Again, there is a very nice opinion matter in environmental science and technology from a Chinese group, where they say that these nomadic tribes, local people, they actually burn woods and all to keep them warm, and those are actually kind of have a very detrimental impact on the melting of the glaciers. So yes, to one line answer to your question, it is, at least in Chota Shigri Glacier, we should be more concerned about the local pollution, local level pollution, than overall pollution and pollution from Indo-Gangetic plains. Then the sixth question from Uday Sharma. What is the reason behind the less, almost negligible concentration TOC, rhenium, osmium, just a little above the lower ablation, upper ablation margin line at around 4750? To answer that, as I said, that there is a lot of spatial variability. Like for example, if you go to more over the ablation zone, above the snow line, close to the accumulation zone, what we see that immediately the mafic contribution increased. So please think of it as a box which is a mixture of material coming from different sources. Now, one possibility could be that you have a organic to TOC content of 1% on that particular hole, but all of a sudden, because of something, you are adding more of other material. So basically, you are diluting the TOC signature. So it is not that the TOC was not there, but simply you have added maybe several kilogram of local dust, your concentration level has decreased. So that may be one of the reasons. So it's a very heterogeneous system. It is not a closed box where only a percent from some percent from A, some percent from B, and some percent from C it is moving in. It's a mixture of all these different components which actually finally give you the concentration values.
Yeah, thank you, Dr. Sen. I think you have all answered all the questions, and thank you very much for a very nice webinar that you have offered. Thank you for sparing your valuable time with us in the MOES webinar. Thank you very much.
Okay, thank you very much. And again, thanks to MOES for giving me this wonderful opportunity to talk about our research activities in IIT Kanpur.
Yeah, and there are more questions from the audience, but they can get to you through email and take the discussion.
Sure, yeah, please write to me if you have any particular question. I would be happy to answer over emails.
Yeah, thank you. Thank you very much.
Okay,
Yeah,
thank you
we
so
can
much.
go offline. Yeah.
Okay.